Welcome to Weird Climate. We're going to talk about climate change today in a lot of different ways. We're going to address the evidence, the causes, the effects, and some of the solutions for climate change. The first thing that we want to talk about is what is climate change? My name is John Dutton. I am a science teacher at Campus International High School.
My name is Jason Tout, and I teach environmental science and chemistry at Campus International High School.
What do you think climate change is?
So to me, the important thing to understand is climate refers to the average global weather over time, not just at one single instance. It's not what's outside your window right now, but what is the overall average of everything going on in the world over a period of time.
We're talking mostly about temperature and precipitation. Those are the things that we measure, that we look at, and that are changing most of all, that end up impacting all of humanity. We're talking about how precipitation changes on Earth. So places that typically get a lot of rain, they get more rain with climate change, and typically places that don't get a lot of rain get even less. In other words, wet places get wetter and dry places get drier.
Because I, like most people, like to eat, and I like to know that my home is going to be where I left it. Agriculture is dependent on us being able to predict and expect consistent weather patterns. One thing that we associate with climate change is alterations in those weather patterns and increased extreme events.
And so what do you mean by an extreme event?
So extreme weather events include hurricanes, floods, droughts. We oftentimes talk about these things in terms of a 100-year flood, because we would expect to see a flood of that magnitude every 100 years.
But why does that affect me? In Cleveland, we're not getting hurricanes. It rains a good amount all the time. And, if it floods, it goes away really quickly. How does that affect us here in Cleveland?
Well, the reality is what we eat now is based on a global system of transporting our agricultural goods. So most of the food that we consume isn't actually grown in Cleveland or Northeast Ohio, or even Ohio, right? We don't have the ability to grow bananas here. Whether in Florida, whether in California, whether in China or Japan or Costa Rica, all of these places that does have an indirect effect on us here in Cleveland.
A lot of people, when they hear climate change, they hear global warming, and they hear that temperatures are going up. Does climate change mean that it's getting warmer everywhere?
Definitely not. The idea of global warming refers to average global temperature is going up. Some places may actually get colder. Some places are going to have inconsistent weather, like Ohio, and some places are going to get warmer. But overall, the planet is getting warmer. If you collect all of the data from all of the cities and all of the countries, that the average temperature is increasing.
I think it's also important to keep in mind that not only is the average temperature increasing, but the average amount of energy in our atmosphere is increasing. And that's what leads to the things that you just talked about, the hurricanes and the floods and the droughts. When you have more energy in the atmosphere, that means that you're going to have more evaporation, and you're going to have more active thunderstorm cells, and you're going to have generally more active weather that happens as a result of that. So this first section, we're going to talk about the causes of climate change. So what, Mr. Tout, are the main causes of climate change?
Well, climate change is, we associate with the greenhouse effect, which is driven really by three molecules, three main molecules we're going to focus on in our atmosphere. Water vapor in our atmosphere, but water in general is associated with the albedo effect, and different states of water, solid water, liquid water, and water vapor have different reflectivity. Methane and carbon dioxide, the one most people have heard about, are both major players in the carbon cycle, and all of these combine to have a major warming effect, which we call the greenhouse effect.
And so today in this section and in all the sections, we'll be presenting a wide variety of demonstrations, experiments, and other things that we've done and that we've also done with students. So you'll have an opportunity to interact at least a little bit and understand the information, hopefully even better than just hearing it from our mouths. Today we're talking about the carbon cycle, and we are going to compare the carbon dioxide output of the RAV4 XLE with the matrix. What we're going to determine is the amount of carbon dioxide coming out of the tailpipe by attaching a garbage bag to the tailpipe, and we'll see how quickly that 30-gallon trash bag fills up. First, let's turn on the RAV4 and see how quickly that fills up, keeping in mind that about 14% of that exhaust is carbon dioxide.
3, 2, 1, go.
As we watch the garbage bags fill up, let's talk really briefly about how much a metric ton of carbon dioxide costs the environment.
All right, stop.
According to the EPA, 1 metric ton of carbon dioxide costs the environment between $12 and $123. Depending on what that money is spent on, it can actually help improve the damage that comes from putting carbon dioxide in the atmosphere. So let's do some quick math. It turns out that the RAV4 took about 12 seconds to fill up that 30-gallon garbage bag. Well, the matrix took 32 seconds to fill that up. Our question that we want to answer is how long will it take the RAV4 to produce 1 metric ton of carbon dioxide? So let's start off by converting. And what we can do is we can take 30 gallons per bag, per garbage bag, multiply that by 3.8 liters per gallon because we want to have metric. We take that 14% and we can express it as 14 parts of carbon dioxide per 100 parts of exhaust. And then we can multiply it by the density of carbon dioxide in order to get that from liters to grams, 1.96 grams in 1 liter of carbon dioxide. We can cross off the units as we see here so that we don't have extra units. What we end up with is 31 grams of carbon dioxide in 1 bag of exhaust. And in order to get metric tons, what we can do is convert that to kilograms, 1,000 grams in a kilogram, and then we can convert it to metric tons where there's 1,000 kilograms per metric ton. We get rid of all those units that are on the top and bottom, and we end up with 3.1 times 10 to the negative fifth metric tons of carbon dioxide per bag of exhaust. Finally, let's figure out how many hours it takes to get that metric ton. So what we can do is we can take that 3.1 times 10 to the negative fifth metric tons of carbon dioxide per bag of exhaust, cross off bag on both sides because we're dividing it by the 12 seconds it took, and then we can flip that number. All right, and when we flip that number, it'll end up with 3.8 times 10 to the fifth seconds per metric ton of carbon dioxide from that RAV4. And we want to convert from seconds to hours, so we take 60 seconds in a minute and 60 minutes in an hour, and we end up with a grand total of 110 hours in order to produce 1 metric ton of carbon dioxide from a RAV4.
In this section, I'll be showing you an experiment and explaining about the concept of albedo. Albedo is how much light is reflected off the surface of Earth. A high albedo refers to a large amount of sunlight that is reflected. A low albedo refers to a low amount of sunlight that is reflected. So one way that we can actually test this is by having simply 2 different colored pieces of paper, a white piece of paper and a black piece of paper, on a hot day. I have both of these in my garden on top of a bench. And so what I am doing is I'm feeling underneath to feel how much heat there is. And then I'm going to use the temperature probe to actually determine what the temperature is underneath each piece of paper. At 0 minutes, the black piece of paper was at 48 degrees Celsius. And then after 10 minutes, it went up to 54 degrees Celsius. And finally, after 20 minutes, it was up to 58 degrees Celsius. That's pretty warm. Now let's check the white piece of paper. We would expect that one to be a little bit cooler. At 0 minutes, it was 43 degrees Celsius, And then after 10 minutes, it went down a little bit to 42 degrees Celsius. And then at 20 minutes, it went down to 38 degrees Celsius, showing that most of that sunlight did in fact reflect off of that white surface. Looking at a diagram of albedo, we see that albedo quantified can range from 0 to 1. The highest albedo is snow on ice at a value of 0.9. We see that soil has a very low albedo at 0.2, where it is reflecting only a small amount, so that means soil is actually absorbing most of that sunlight that hits it. And then the open ocean has a very low albedo. Water is really good at absorbing sunlight, not only because of its color, but because of the nature of the molecules, the water molecules, so that ocean is at 0.06. And finally, sea ice is actually at 0.6, which means that it's really good at reflecting most of that sunlight back into the atmosphere. So what does this mean for climate change? Well, as ice in the ocean and on land melts, that means that the albedo of that land is going to get lower. And specifically in the ocean, as that ice melts, the albedo is going to get super low. That means that more and more sunlight is being absorbed by the Earth, and less sunlight is being reflected out into space. The more sunlight that gets absorbed by Earth, the warmer Earth gets, and the more that climate change accelerates.
In this section, we'll be discussing the greenhouse effect. The greenhouse effect happens due to gases in the atmosphere trapping heat in the atmosphere and therefore on Earth. And it affects the air, the land, and the water, all in different ways. And now we can do a quick experiment with the greenhouse effect. First, take 3 bottles, make sure they're empty and clean, and then mark them a little bit of the way up. We're going to fill each of these bottles with a different substance in order to measure different parts of the Earth. The first bottle is going to get soil in order to measure land, part of the Earth. What we'll be doing is measuring the temperature of the air above each of these 3. And then the second bottle we will fill with water. And then the third bottle we're just going to leave with air. And then we're going to put plastic wrap, and I used a rubber band to hold that plastic wrap on top of each one to represent the atmosphere. Now the temperature, the ambient temperature of the air was 34 degrees Celsius after 5 minutes. Then I measured the temperature of the bottle containing just air, and that was 32 degrees Celsius. And then the temperature of the bottle containing water is 32 degrees Celsius as well. And finally, the temperature of the air above the bottle containing soil to represent land was 35 degrees Celsius. I waited a few more minutes, and then my ambient air temperature after 10 minutes was 40 degrees Celsius, and that same ambient air temperature after 20 minutes was 39 degrees Celsius. So I went ahead and measured the temperature of the air, the bottle with air. It was 34 degrees Celsius after 10 minutes. After 15 minutes, it was 38 degrees Celsius. And then after 20 minutes, it remained at 38 degrees Celsius. The second bottle, the water, I measured after 10 minutes, it was 33 degrees Celsius. And then after 15 minutes, it was 38 degrees Celsius. And finally, after 20 minutes, it was 38 degrees Celsius. Lastly was the one representing land. After 10 minutes, it was 35 degrees Celsius. After 15 minutes, it went down a little bit to 34 degrees Celsius. And then finally, after 20 minutes, it was 41 degrees Celsius. And overall, the temperature on the land increased the most to 41 degrees Celsius, which reinforces the fact that climate change affects land temperatures the most out of all the places on Earth.
In our next segment, we're going to discuss some pieces of evidence for climate change. So, Mr. Dutton, what are the main pieces of evidence and which ones are we going to address today?
So carbon dioxide levels are a huge piece of evidence for climate change. Carbon dioxide levels and temperature tend to follow each other over time. But in order to be able to get the bigger idea and the bigger record for how carbon dioxide levels have changed over time and temperature has changed over time, we need to look into the historical record. And humans have only been keeping track of carbon dioxide levels and temperature for about the last 60, 70 years. So we have to look at other pieces of evidence. So what we're going to be looking at today are tree rings and ice cores and glacier records, how the ocean temperatures get affected, and how that impacts sea level. So all of those help us understand the current evidence and the historical evidence for climate change.
So if our records only go back 60 years, how far back can we actually see?
Well, it turns out that given ice core data, we can actually look back hundreds of thousands of years into the past because snow keeps falling in places like Antarctica and it builds up over time, and we can drill what are called these ice cores, and we can actually expose those gases from hundreds of thousands of years ago in order to get some idea about what the atmosphere was composed of at that time. So let's get started.
In this video, we're going to discover some evidence for climate change in tree rings and ice cores. Tree rings are found when you chop down a tree like this. This is courtesy of nasa.gov. And so we can look at that cross-section of a tree and we can see quite a few interesting things. For example, every time it's a rainier season, that ring, that spacing is going to be bigger than in a dry season. We can also see what happens if there are forest fires or other traumatic events for the tree. And so it gives us a window into looking back in time and being able to tell a better story of what happened before we started measuring things on Earth. We can also look at ice cores, and an ice core is a sample that has been drilled from a large packed ice area like in the Antarctic. That's where Ars Technica is going to take us, and they are going to demonstrate how it is that we are able to tell the story of the past from these ice core samples that they drill.
So the South Pole Ice Core has a couple of main goals. One of those goals is to get like ultra trace gases. And so the reason this is a good site for it is that it has a unique combination of being very cold because it's so far at the pole, yet has a relatively high snowfall. We kind of talk about the ice in three parts. So the upper part is bubbly ice. Bubbles are clearly visible. Then we have a section that we call the brittle ice. So this is where bubbles are still visible, but they're getting smaller and they're under pressure. So when you bring them up to the surface, they want to expand and crack the ice. Now, once you get below a certain depth, those bubbles have actually all diffused out into the ice lattice.
Our portion, we do the chemistry on the ice core. The primary purpose of that is to date the ice core. So you get seasonal changes in different chemicals in the ice for various reasons. And if you can get samples small enough, you can actually see those changes and then count annual layers going back in time.
The core will contain 50,000 years of climate history, and so that takes us through three big time periods. So the most recent, roughly 10,000 years.
We processed down to 734 meters continuously, and when we stopped at 734, that was about 10,200 years or so. So just about to the end of the Holocene.
That's kind of the stable, warm climate that human civilization has developed in. Between roughly 10,000 and 20,000 years ago was the transition from the last glacial maximum to today. So that's about a 3 to 4 degree C global temperature change. And then the period from kind of 50,000 to 20,000 years is what we call a kind of glacial climate, so much colder than today, though not quite as cold as the last glacial maximum. And it's a period with abrupt climate changes in it.
We've tied it to volcanoes that we know absolute dates for, and it matches really well.
And so this is one way that we can begin to look at not just what the climate changes were, but how they happened. And so it's those kinds of questions that, we're drilling ice cores to help answer so that we can really understand, timescales on decades relevant to human lifetimes of how the climate system interacts and responds, and use these natural climate variations that are big to understand what's going to happen.
Let's talk about glaciers. This is a
Water melts off and goes underneath it, and then the glacier uses that as like a lubricant between it and the ground so it can move.
This is a constant process. This is normal. Glaciers move all the time. Unfortunately, because of climate change, what's happening is that glaciers are receding faster and faster. So this is a glacier in Alaska. You see these two pictures are about 100 years apart. Massive glacier in 1909 and completely gone. And this is just a lake at this point in 2004. And that was 16 years ago at this point. Go to the Rocky Mountains in the western US. We see the same thing happening, again, about 100 years apart, these two pictures. And now there is a lake at the bottom of this glacier where it was just pure glacier before. Go down to the Andes in South America. We see the same thing happening. So this is not just a northern hemisphere thing. This is happening in the southern hemisphere as well. And that was just over the course of about 40 years. There's a couple of these glaciers that we're going to see that have receded in a very small amount of time. Glaciers also exist all over the world on the tops of mountains, like in the Alps in Europe. And what we see here is that over the course of 45 years, these glaciers have receded almost completely. Mr. Tout, didn't you experience this yourself?
I actually climbed it over the course of a 5-day hike. No technical climbing. But it was a backpacking trip, effectively. It was interesting learning about that glacier, while we were going up it, to the point where, like, at this point, you can get almost to the top of the mountain before you really see any snow or any ice. In 1993, that was not the case.
The Himalayas on the border between India and China, huge differences just over the course of a little over 50 years. In Indonesia, over the course of about 70 years, almost no glacier is present on this particular range. What do we mean by albedo?
Albedo is when light reflects off of.
So I hear you saying that light is reflecting off of ice. Sunlight will also be absorbed by what on Earth?
Water.
So the fewer glaciers there are, the more heat that's going to be absorbed on Earth. So what is something that happens when glaciers melt more than they freeze?
Water levels start to change.
Where does that water end up going?
The ocean.
What is the impact on the ocean?
Sea levels will rise.
In this section, I'll be performing an experiment for you, comparing what happens with an iceberg to a glacier. So the one on the left is going to represent what happens to an iceberg in the ocean. The one on the right is going to represent what happens to a glacier on land. I start off by measuring the temperatures of both the iceberg and the glacier. The iceberg is at 20 degrees Celsius. And then I measure the water in the glacier, and it turns out that it's also 27 degrees Celsius. It's good to always have those initial measurements. And then what I do is I put 2 cubes of ice, both in the iceberg and on the glacier. Those 2 cubes of ice are going to melt, and the one in the iceberg is actually not going to change volume. As you see that mark that I put on the glass, the water volume for the iceberg one is not going to go above that level, and we see the water level for the glacier container is actually going above that level, meaning the water that melts on land is actually raising that water level. So the final temperature for the iceberg after the ice melted was 17 degrees Celsius. And I have to wait a little bit longer to let the ice melt for the glacier. And what we're going to notice is that water temperature is going to be a little bit higher because most of the melting happened while that ice was still on land. So it ends up with a final temperature of 24 degrees Celsius. So the lesson here is that ice that melts in the ocean does not raise overall sea levels, while ice that melts from a glacier that flows into the ocean does in fact raise sea levels. Finally, the heat that actually melts the ice for the iceberg is coming mostly from the water surrounding it, And the heat that's melting the ice on land in the form of the glacier is actually mostly coming from the sun and being reflected off of that land.
One of the things I couldn't help noticing on my trip to the aquarium was how it sits right on the water. And while I was sketching, I noticed certain unusual features. For instance, this ramp around the aquarium slopes slightly up. So when I got back to my studio, I looked this up online and I found out that this ramp goes up by design to make room for the rising waters that will happen around the globe in the 21st century. That's Bud Riss, president of the New England Aquarium.
And what that means is, over the next several decades, the water is going to be at least 1 to 2 feet higher than it is today.
So why is the water inevitably going to rise?
Well, start by thinking of the ocean as a dance floor. You see, under normal temperatures, the ocean's water molecules move like they're doing a slow dance. Nice and easy. And a lot of them can fit on the dance floor. But pump up the jam, and every one of those molecules starts moving, pop-locking, getting down and taking up a lot more room on the dance floor. That spacing out of faster molecules is exactly what thermal expansion is, and one of the major reasons oceans will rise in the 21st century as they inevitably heat up.
Nice. Got it.
In this section, we're going to talk about the effects of climate change. So, Mr. Tout, can you talk real quickly about what are some of the main effects of climate change?
When there are changes in the water cycle, such as dry places getting drier, wet places getting wetter, that has many impacts. It's easy for me to come back to food. I want to know that I'm going to get the meals that I want or the food that I want and need. When there are changes in the water cycle and temperature, it affects our agriculture systems, our ability to grow the foods that we've been growing. Certainly just increases in temperature have broad effects on our ability to maintain homeostasis. That increase in temperature also has an effect on the spread of diseases. When you look at the effect on biodiversity, the more diverse an ecosystem is, the more complex a food web is, the more sustainable it is, the more able it is to respond to, say, an extreme weather change and recover after some major event. As biodiversity decreases, which is one of the main effects of climate change, is species are dying off.
And so which are the 3 areas of our focus today?
Climate versus weather, infectious diseases, and temperature as main effects of global climate change.
Okay, so if we scientists are so good at making these dire long-term predictions about the climate, how come we're so lousy about predicting the weather? Besides, this year, we had a colder winter in my town. For all the scientists know, we could be in for global cooling. Here's the difference between weather and climate. Weather is what the atmosphere does in the short term, hour to hour, day to day. Weather is chaotic, which means that even a microscopic disturbance can lead to large-scale changes. That's why those 10-day weather forecasts are useless. A butterfly flaps its wings in Bali, and 6 weeks later, your outdoor wedding in Maine is ruined. Climate is the long-term average of the weather over a number of years. It's shaped by global forces that alter the energy balance in the atmosphere, such as changes in the sun, tilt of the Earth's axis, the amount of sunlight the Earth reflects back to space, and the concentration of greenhouse gases in the air. A change in any of them affects the climate in ways that are broadly predictable. My friend's meandering represents the short-term fluctuations. That's weather. It's almost impossible to predict what will attract his interest next, but not hard to know what the range of his meandering will be, because I'm holding him on a leash. We can't observe climate directly. All we see is the weather. The average weather over the course of years reveals a pattern. I represent that long-term trend, which is climate. Keep your eye on the man, not the dog.
welcome to another episode of It's Infectious, the game show that connects you to a new disease every day. Today's panel is 4 all-star students from Campus International School, and they've decided to challenge their notorious science teacher. We have 6 questions between them and their evil teacher to see who can come out on top. Panelists, are we ready to begin? Question 1, why can't we use antibiotics to treat coronavirus?
We can't use antibiotics to treat coronavirus because coronavirus is a virus and antibiotics only work on bacterial infection.
Excellent work. That is worth 12 points. Congratulations. Question 2, how do we cure viral diseases?
One reason we can't cure viral diseases because they mute too quickly. However, our bodies will, immune system will develop antibodies to the virus. The only way to cure a virus is to achieve herd immunity, either through vaccinations or the majority of the population surviving the infection.
Excellent work. That is worth 42.5 points. We're going to move on to question 3. Why has the increase in the human population led to urbanization? And why don't we just spread out?
The increase in human population led to urbanization because people are moving from rural areas to urban areas.
Excellent work, Ayana. That is 26 more points for your team. Mr. Dutton, it's okay. You only have to make up 80.5 points right now. How does urbanization lead to an increase in infectious diseases?
Turns out that urbanization is the fact that more and more people are living in densely populated cities. So since people are closer together, they're more likely to pass, diseases back and forth, and the disease is more likely to get spread before the person gets over it. And there's your answer.
Excellent. That is worth all 19.5 points, bringing their total to 100 points. Well done. All right, Mr. Dutton, I just feel bad for you. So this next question was really only worth 5, but I'm going to make it worth 100 just for you.
I appreciate that, Mr. Tao. I'm going to do my best.
Can you make sure your buzzer is working? All right, question 5. How does climate change force people into unhealthy or unsanitary living conditions?
Oh, I got this one. All right, so climate change is often associated with like things like extreme weather events like hurricanes, like what happened with Hurricane Katrina. And so entire communities can be displaced. They can all end up in the same place together. And it can be really difficult for people to have clean water or to keep any sort of social distance. We're heading into hurricane season right now, and so this is something that people are really concerned about with coronavirus.
You just got 100 points, and all I had to do was turn off everyone else's buzzer. It's all tied up, 100 to 100.
All right, good game, guys.
There is one more question, however.
Oh no.
And as is customary, the year is 2020, so it is worth 2,020 points. Question 6. How are climate change and infectious diseases, such as coronavirus, linked?
Climate change leads to more frequent outbreaks of diseases.
And severe weather events can lead to the massive migration of people and put them all in one place.
And of course, when people are migrating, they're migrating away from, their access to sanitary water.
They are crammed together, so then that makes them more prone to catch diseases.
Congratulations, Campus International students. Excellent work on that difficult question 6. Sorry, Mr. Dutton, that buzzer means you're out of time. And this has been another episode of It's Infectious, introducing you to new diseases every day.
Now let's talk about carbon dioxide levels and temperature. The relationship between those two things is really important. First of all, climate.nasa.gov gives us a lot of really great information about temperature and carbon dioxide levels. As you see here on the left, we see that temperature has been going up steadily for the last approximately 100 years. A lot of that can be attributed to climate change. And so what we are focused on as far as this graph is concerned is the average between 1951, and 1980. That's what all the other temperatures are compared to. So when we talk about the temperature is increasing, that's the average that we're looking at. Let's zoom in on part of this graph, the last 20 years. And what we see here is that temperature on Earth has been increasing so much that it's almost 1 degree Celsius over that average. And over the last 20 years, it's increased over 0.5 degree Celsius. Another way of looking at this temperature change on Earth is through a time-lapse image of the relative increase in temperature on different parts of Earth. And as you see the years increasing in the upper right-hand corner, we see that not everyone on Earth is experiencing the same temperature rise. Specifically, what we can see is that in the northern latitudes near the North Pole up here, that the temperature difference is extremely different than everywhere else on Earth. And you should also see this difference between land and ocean. And so as we get closer to present day, what we see is that temperature anomaly or temperature difference by the poles gets to be about 4 or 5 degrees different than in that average range of 1951 to 1980. And there's that difference right there becoming really obvious. This is the world we now find ourselves in, where we see overall throughout the entire globe, there is a massive temperature difference. Does anyone have any ideas as to why there's a big difference in temperature in the northern latitudes, specifically near the North Pole?
Well, part of the reason is because there's a lot of ice in the North Pole, and because of the albedo reflecting off the ice and melting the ice, and then there's more water that can absorb the heat and the light, and so it's warming up at a much faster rate up there.
Excellent, thank you. And as we see, there are pockets of ocean that are still at average temperatures, and water holds on to heat a lot better than land does. And so that's something else to consider when looking at these maps. Let's talk about carbon dioxide, because that's the other half of this picture. As of last month, carbon dioxide levels worldwide at Mauna Loa Observatory in Hawaii, which is the main observatory used, were at 417 parts per million. And what we see the general trend happening is that carbon dioxide levels are doing what?
Carbon dioxide levels are rising.
Excellent. And what is the other trend that's happening on an annual basis? What do you see happening here?
It fluctuates.
Excellent. Does anyone know why that fluctuation happens over the course of a year?
It's because of like the growing of plants and such. Because the spring they like bloom more and they're growing, so they're getting more carbon dioxide out of the air and putting more oxygen into the air. But then during the winter, the carbon dioxide levels start increasing again because there isn't everything's covered in snow. Everything is toned down for the winter because it's cold and stuff.
Excellent. A common question at this point is like, but this is for all of Earth. The northern hemisphere has so much more land area that it outweighs the effects in the southern hemisphere. As we're entering summer now, the southern hemisphere is entering winter, but because there's so much more land, there's so many more plants that are taking up carbon dioxide, that's what accounts for this effect, this bouncing up and down over the course of the year. This is accounting for that effect and is taking a running average. So this black line is more reflective of overall carbon dioxide levels, not taking into account what's called seasonal variation. So we see that seasonal variation over here on the bigger graph. That's giving us over 60 years of data. And then the black line again is giving us that rolling average that helps us understand a little bit better what's happening over longer periods of time. And finally, if we compare what's happening with carbon dioxide levels with temperature, then we see that both are in fact increasing over time over the same time period. There are little variations, but ultimately the trend is up. What are your predictions for global levels of carbon dioxide and temperature? I guess in your lifetime, what do you think? What are your predictions?
I feel that technology advancing, there's going to be people trying to prevent the advancement of CO2, but at the same time, I feel like we've made it so far with it increasing that it's going to be hard to completely prevent and to reverse it.
Yeah, I agree with Alanis. I think that it may eventually go down, but we're going to have to put in a lot of work for it to be able to go down because it's not going to happen immediately.
With like the technological advancements, maybe we easier to predict and find better solutions that can be beneficial to decreasing the CO2 in the atmosphere.
And what do you think about how coronavirus might have an effect on carbon dioxide?
I mean, people are still, driving. It's not going to have that much of a change because we've always been very consistent with having such a high level of carbon dioxide in the air. And just because we're being quarantined doesn't mean that's going to be immediate change.
Excellent, thank you. And then finally, what would happen to global temperatures if carbon dioxide levels dropped to below 350 parts per million tomorrow?
Even if we manage to drop CO2 levels to below 350 CC by tomorrow, the temperature, like the overall temperature of the Earth, would continue to increase because it's got like all that momentum behind it. Like it's been going up for so long, even if we decreased all the CO2, like right now, the temperature would continue to increase for years to come.
Wonderful, thank you so much. So hopefully this gives you some more information about the link between carbon dioxide levels and temperatures on Earth.
Some studies have shown that studying climate change has actually led to increased rates of depression. The belief is that that is because we beat you over the head with all of the negative impacts from climate change. So it's important to take a minute and talk about the solutions to climate change and hope for the future, because there is some. Mr. Dutton, what are some of the main solutions?
One of the first solutions is to get rid of fossil fuels. This is stop using fossil fuels. They're the major contributor to carbon dioxide in our atmosphere. Something else that we can do, because getting rid of fossil fuels is a gradual process, something else we can do is to be more efficient about how we use energy so that we are not cooling down areas, like we're not turning on the air conditioning to 67 degrees during the summer. Maybe you're only air conditioning an area to 72 or 75 degrees. Maybe during the winter, you are heating an area to maybe only 67 or 68 degrees so that you are using all of our resources more efficiently. We also can cut down how much we're consuming, and that means consuming resources, consuming goods. All of those things require energy, and energy typically is one of the major reasons that greenhouse gases increase in our atmosphere. Another thing that we can do is to eat less meat, because raising livestock is a major contributor to greenhouse gases. And also family planning and generally having fewer children is a way to ensure that fewer resources are being used, because for every human on the planet, there are more resources that are being used for that human to live.
With all of that in mind, which ones are we going to address of our session today?
So we're going to talk about three major things. We're going to go over the different ways that we can produce energy that doesn't involve fossil fuels. We're also going to take a look at what a solar oven looks like, something that you can actually build yourself with household materials. And finally, we'll take a look at what a different mix of energy and all sorts of climate change solutions looks like when you put it all together, and we'll have the students come back and show us what their solutions are.
We're going to discuss three types of alternative energy: wind power, hydroelectric power, and solar power. The first type is wind power. Here's a wind turbine at Case Western Reserve University in Cleveland. Some facts about wind power. First of all, it is 4,000-year-old technology. This is old technology. This is nothing new. It is possible that one turbine like this can power over 500 homes. As you can see, there's no water required with wind power. It can be installed in lakes and the ocean. So for example, it could be installed in Lake Erie. It can be as tall as 200 meters, over 600 feet. Those blades that you're looking at can move up to 200 miles an hour. As far as all the countries on Earth, Germany leads all countries as far as installation of wind power, and wind power provides more jobs than other forms of energy. Now on to hydroelectric power. I traveled to Hetch Hetchy Reservoir a few years ago. Here I am in front of the reservoir. It's a big body of water in front of a dam. And so you can see the dam here. There are turbines inside that spin, that produce electricity, and water flows out. This is a spillway on the side of this dam. And then below the dam, you see water coming out into the river that continues on to San Francisco. In Cleveland, we have a dam. We do not have hydroelectric, but we do have a dam here, like Lakeview Cemetery. There's some others. Some interesting facts, among others, Niagara Falls was the first hydroelectric power in the US. 50% of renewable energy is hydroelectric, and we can pump water uphill and then save it for later when we allow it to flow downhill, which can actually reclaim a whole lot of electricity. Finally, we have solar power. Right now we're looking at the solar power plant in East Cleveland, and it's owned by MCCO Lakeview. It is a fact that 1 hour of sun that hits the earth is enough to power the entire world for 1 year. So it's really important that we install solar panels in order to be able to capture that energy. California Solar itself powers over 4 million homes. It's a myth that solar needs direct sunlight. It can actually operate in indirect sunlight. Solar reduces carbon dioxide by 100 tons over 30 years, and that is just a home installation. And solar can power cars, trains, and airplanes. So if you have something like a Tesla at home, as we take a look at the entire solar plant, if you have something like a Tesla or an electric car at home, you can actually power that by charging it at home with solar panels and then running it for a full day.
What we're going to do today is we're going to build a solar oven. You need a big old box, some plastic wrap, some aluminum foil. You need some packing tape. You're also going to need some newspaper and a smaller box to fit inside the larger one. We are going to cover the outsides with the aluminum foil, and we're going to do the same with the box. We're going to fill this area right here with newspaper, and that'll act as insulation. Don't get distracted by the newspaper. I just started reading an article about Alex Trebek. You can tell I'm a master at wrapping Christmas presents. And one more thing, it is easily recyclable. You can wash it, you can use it as a scrub brush. So the little box is done. In order to make sure that these big old flaps reflect the sunlight down into the small box as much as possible, the way light works, the angle of incidence is equal to the angle of reflection, which means that whatever angle the sunlight comes in at, it will bounce off at that equal angle. During the summer months, the sunlight is almost directly overhead. If we want the sunlight to bounce down here, then we need to think of what angle is it that it comes up, and then make an equal angle with straight up into the air.
So now I'm testing out the solar oven. I have some plastic wrap, my nemesis, over a mixing bowl full of water. The temperature has gotten up above 60 degrees, so there's a lot of condensation on the inside of that plastic wrap. Don't be in a hurry to cook anything. Been out here for 3.5 hours now, and the water is definitely warm enough to be cooking something. You won't be having dinner at the drop of a hat, that's for sure. But just some cardboard and tin foil, and we're able to cook things. It's pretty cool.
So now we're going to play a different kind of game. This is called the Stabilization Wedges game. And this is how we can simulate how we might be able to reduce carbon dioxide levels on Earth through a variety of strategies. Specifically, you're going to choose 8 strategies. Each of those 8 strategies will be responsible for reducing carbon dioxide levels by 1 billion tons. 1 billion tons every year for 50 years. And so that's why over here you see 50 years. And then each of these wedges reduces another 1 billion tons every year in order to get us down to the point where we are flattening how much carbon dioxide is being put into the atmosphere, so that we get to where we're not adding any more carbon dioxide effectively to the atmosphere that can't be pulled back out through natural means. You guys are going to be split into two teams, Ayana and Alanis. You are, say your team name real quick.
Amazing.
All right, and Vivian and Arden, you are going to be team
Fabulous.
So we're going to put you into breakout rooms, and you will be able to determine a strategy to figure out which 8 of these wedges are the best for you, taking into account the cost, the challenges, and of course, what the actual strategy is. Keeping in mind also that in order to cut 1 billion tons of carbon dioxide, this is a difficult thing to do, and so it requires sometimes it requires a lot of sacrifice on the part of people. Sometimes it requires a lot of money. Something to keep in mind if you want to play at home, I have a couple links for you. cmi.princeton.edu/wedges is a link that you can follow, and you can see all the information that I have here. I've also put together a worksheet that you can use. It's at bit.ly/stabilization wedges. Make sure you capitalize the S and the W, and you can play along with what you see the students doing in this game. Let's go ahead and divide up. All right, so Team Amazing and Team Fabulous have chosen their strategies. So let's start with Team Amazing. If you guys can briefly describe a couple of the outstanding strategies that you chose and why you chose them.
So out of the 8 strategies we chose, I think the 2 most important ones are CCS hydrogen and wind hydrogen. And CCS stands for carbon capture and storage. And basically the reason why we chose the 2 is because they overlap in a way. Obviously they both have to do with the production of hydrogen, but CCS hydrogen produces hydrogen at 10 times the current rate. And wind hydrogen will eventually power half the world's cars predicted for 2050 with hydrogen. The only problem is there's some safety issues with the CCS hydrogen, and for wind hydrogen, you can't really, it's a not in my backyard type of thing, but.
What did your team think about how environmental groups and industrialized governments would consider your particular set of strategies?
For environmental groups, we decided that they were going to be more open to these changes for the environment and for people using them. And for they're already established and set in their ways, then because they also have a set of the technology that they already use with our current, manufacturers and everything, they might be a little stubborn to change.
All right, great job, Team Amazing. Let's move on to Team Fabulous. So, can you briefly describe your outstanding strategies and why you chose them?
We chose a lot of methods that involved increasing the efficiency of things like buildings and transportation and such, because people might be more willing to embrace those kinds of ideas since they're not they're not too radical, and we're already starting on those processes. So, and efficiency is effective. I love efficiency. We also chose solar electricity because from what I've read, it's like constantly being developed. So even it's expensive right now, but it'll get gradually less expensive over time. And people seem to be really interested in solar energy at the point in time that we are at this point in time. So people might be more willing to embrace that kind of change as well, even though it's more expensive.
Wonderful. And so how do you guys think that environmental groups and industrialized governments would interpret this set of strategies?
Well, for environmental groups, we chose 5 because all of our strategies that we picked are very environmental friendly, and they're safe. And we chose a 3 for industrialized governments because we didn't really know which side they would be on. It was like a 50-50 kind of thing, because one, it would be easy to convert to all of these strategies, but some people may not want to do them, which is why we chose a 3.
Wonderful. Excellent job, Team Fabulous. That brings us to the conclusion of the Stabilization Wedges game. And I hope that you understood quite a bit, or you got to understand quite a bit about the different strategies that are available in order to increase efficiency and to reduce carbon dioxide output on Earth in order to help mitigate the worst effects of climate change. In case you want access to this presentation or any of the other materials that you saw today, you can go to bit.ly/weirdclimate2020. To the 4 students who joined us, Alanis, Vivian, Arden, and Ayana, we greatly appreciate it and all of your hard work. This video couldn't have been possible without your participation and hard work. Mr. Tout, did you have any concluding thoughts for us?
Just to say thank you all for tuning in, and thank you again to our 4 contestants. We could not have done this without you guys.